So today we are going to discuss ray optics. Fine. So when we discuss about ray optics, we always assume that light is a particle. Fine. And if it is a particle, it will travel, straight line. Its path will be well defined. You will be able to track what is the path of the light, and like that, the way the particle travels. So you will be able to see the path as a straight line. And until it hits an object, or suppose there is a reflection, its path won't be changed. Fine. So it will travel in a straight line. Fine. So we have discussed about reflection as well as refraction when it comes to ray optics. Fine. Few of you can sit there. Two of you can sit there. You two. So that I don't only look this side. Okay. So now we have discussed initially itself that light can behave like a particle and light can behave like a wave also. These are the two behaviors of light. Depending on the scenario, light will behave like a ray, and depending on some other scenario, light will behave like a wave. So it's just like human behavior. If suppose some good scenario happens in your life, you will be happy, and in some other scenario you will be sad or angry, or you will be showing different kinds of behavior. Fine. You will be showing multiple kinds of behavior, but light has only two behavior: as a ray and as a wave also. Now, as a ray, we have studied it in great detail. Now is the chance to study the light when it behaves like a wave. Okay. Now, what is a wave? What it is? Wave is a disturbance. Simple. It is a disturbance that travels in a medium or not? It need not travel in a medium. Okay, just a disturbance. Fine. Mechanical waves travel in a disturbance. Have we learned about mechanical waves? In class 11 we have learned about mechanical waves. Fine. So in class 12 we are learning about electromagnetic waves. Light is one of the EM waves. Okay. So it doesn't need a medium to travel. Fine. So we are going to study light as a disturbance or as a wave. Fine. So light, first of all, write down, light is a transverse wave. Okay. Light is a transverse wave. Fine. So whatever basic things we have learned about transverse wave in waves chapter in class 11th still holds good here also. Because the name of the chapter when you studied the waves was waves only, it was not mechanical waves. So we have not just studied mechanical waves in class 11th. We have studied few general things which is true for all the waves, and then few specific things which are true for mechanical waves. Are you getting it? So general things still hold good. Like for example, interference that we have learned, reflection we have learned, all that happens for light also. Okay. Now, although we have done a good amount of study in class 11th itself about wave, but we will not start midway. We will start again from the scratch as if you do not have much knowledge about it. Fine. I am just telling you all these facts so that you will be able to correlate what you have already learned. Then your learning or grasping will be faster. Fine. So, Newton was the one who studied light as a ray. Fine. He was fascinated with the idea that everything behaves like a particle. He had already developed mechanics. So he thought, okay, light is also a particle. So he started understanding light as if it is a particle and studied its all the behavior as if it is a particle. Like reflection and refraction also, he thought that it is the behavior of a particle because of which reflection and refraction happens. Fine. And if reflection and refraction happens because light is a particle, then the speed of light in a denser medium would have been higher. Okay. Why is that? You can Draw an interface like this, and suppose light hits the interface like at an angle of I, then if it is going in denser medium, what will happen? This becomes R, which is less than I. Fine. Now, this interface, suppose this is the interface on which there is a particle that comes in. So light is a particle. Newton said light is a particle. So light is coming like this and hitting the interface. Which direction interface will apply the force? Upward direction, normal direction only. Fine. So the interface can only change the velocity along the normal direction. Interface cannot change the velocity along horizontal direction. Are you getting it? Suppose velocity here is v1 and this is v2. So horizontal component of this velocity is what? v1 sin I. Fine. And its horizontal component will be v2 sin R. Fine. So what will be v2 equals to? v1 into sin I by sin R. Right? And we know that experimentally R is less than I. So this bracket term has to be more than 1. So v2 has to be more than v1. Fine? Right? But later on we came to know, when Newton has suggested all this, okay? When Newton has suggested all this, there was no experiment to check how much speed of light has become in the denser medium. So, but then if Newton is correct, then the velocity of light in denser medium would be more than velocity of light in the rarer medium, which is of course not correct. Fine. So this reflection and refraction Newton has explained using light as a particle. In this chapter we will understand reflection and refraction as if it is a behavior of a wave, and now we will see that it makes sense, because right now if we just use particle theory over here, it doesn't make sense. Is there a proper duster? As in that slightly harder? No? Okay. Anyways, give me a piece of paper. That is much better actually. If you have some rough, don't give me fresh page. Already written rough paper.
So this is
perfect. This is a perfect use of newspaper. You bring only Bombay Times?
This is only in school.
From school, the Hindu. Anyways, so that is why we need to understand the wave theory. Now when Newton was developing this concept, first of all there were very limited resources to check the validity of what Newton is saying. Second, nobody would challenge Newton. Right? So, but then that time also there were few scientists who were developing the idea of light being a wave. Fine. But then whatever experiment they used to propose, Newton had some counter argument. Okay. So, but then there was one experiment, Young's double slit experiment, which Newton could not explain. Okay. That we are going to take up a little bit later. Fine. So my point is that it took years and years and effort to create the concepts of wave optics. Okay, because all the big guys or the big so-called scientists, they were fascinated with the particle nature of the light. Fine. It took a lot of time for wave optics to take shape. Fine. One of the forefathers of the wave optics is Hygen. Fine. He has actually conceptualized everything. Fine. So we'll start this chapter with Hygen's principle. Right? Write down Hygen's principle. This chapter done in school or going on? What is the status? It's going on. Finished. Good. So Hygen principle talks about how wave will behave. How wave will behave given the present scenario. Are you getting it? So Hygen principle trying to predict the future of the wave. What the wave is, what wave will do later at point in time given what it is doing right now. Okay? So that is what we want. Isn't it? You have learned the kinematics, V is equal to U plus AT. You're connecting future with present. So F is equal to mass and acceleration. If you apply force, there will be acceleration. Fine. So you always want something which connect what is going to happen with the present condition. So Hygen is the one principle which connects that. Fine. So this becomes the fundamental theorem, so to say, for this chapter. Alright, so we need to understand it properly. And but then before understanding Hygen principle, we need to understand few terms, because we will be using these terms again and again, not only to understand Hygen principle but going forward also. Fine. First, tell me, you have any example of a wave in your mind? Ripples in the water. What shapes the ripples in white waters are? Circles. Why do you say it is circular? Because you are able to see the circle. And why you are able to see the circle?
Yeah, up and down, you can see the difference.
Up and down as in?
Difference in depth, you can see. You can see the difference in depth of the top portion and bottom portion.
Can you explain a bit more?
Ripples.
Basically what happens, in a circle, all the particles together will move up, all the particles together will go down. Fine? So they are in phase. Are you getting my point? What is phase? What is in phase means? In phase means the phase difference is zero. Getting it? They're together moving up and together they go down. And this is two-dimensional wave. What about one-dimensional wave which is traveling like this? Can you tell me two particles which are in phase? So here are few numbers 1, 2, 3, 4, 5, 6. Tell me any two particles which are in phase.
3, 2 and 5.
What?
1, 3, 2 and 5.
1 and 3.
No, 1 is not.
After some time, what will happen to wave? Wave will move forward like this. Like this. Where this 1 goes, it goes down like this. Where this 3 goes, 3 moves up. So they are not in phase. So which are the ones which are in phase 1 and 4 probably. You can say 1 and 4 probably. Okay, like that. Fine. So the difference in phase between them is actually 2 pi, but then after every 2 pi, anyway things repeat. So you can say that there is no phase difference practically. Okay. So similarly, this is one-dimensional wave, but same thing if it happens in 2D. Like for example, ripples of water. If the particles in a circle, they are in phase, then together move up and together go down. So we'll be able to see the circle. Fine. Write down locus of all the points in phase. Locus of the points in phase is called wavefront. So what kind of wavefront we have when we talk about ripples in water? Circular wavefront. Locus is circle. Okay? So this is the wavefront. Any doubt? What can you tell about velocity of the wave? Which direction it will be with respect to wavefront? What do you think? Perpendicular to the wavefront. Write down. Velocity of the wave will be perpendicular to the wavefront. Velocity of the wave will be perpendicular to the wavefront. Fine. So whenever you see a wavefront, draw perpendicular, you will get the direction of the motion of the wave. Fine. Now, the thing is, we need to first understand different kinds of wavefront. Okay? Can you tell me what is the kind of wavefront a beam will have, a parallel beam of light will have? So like this, so many parallel beam of light comes in like that. Plane. Okay? So the wavefront is plane. Because when I say light is coming like this, it means velocity is like this. Draw perpendicular to velocity, you will get the wavefront. Wavefront is perpendicular to velocity and velocity is also perpendicular to wavefront. Either ways. Okay? What if you have a line, an infinite line, and that emits light in every direction? What kind of wavefront it will have? Cylindrical. Okay? What if it is a point source? Spherical. Okay? So these things should be very clear. Okay? These are like basics, thumb rule. Okay? So now write down Hygen principle. So I'll just dictate word to word as it is written in the book, and then we'll understand what it is written. It's actually 3 or 4 sentences long, so bear with me. According to Hygen's principle, each point of the wavefront is a source of secondary disturbance. Each point of the wavefront is the source of secondary disturbance. Okay? And the wavelets is just part of the wave. Okay? And the wavelets emanating from these points spread out in all directions with the speed of the wave. Fine? Reading it? These wavelets emanating from wavefront are usually referred to as secondary wavelets. Okay, secondary wavelets. Fine. Done. And if we draw a common tangent, to all these spheres. See what I said, every point on the wave is a source. So what kind of source it will be? Point source, it will generate spherical wavefront. So wavelets will be spherical in shape, secondary wavelets. Fine, that is what it is saying. If we draw a common tangent to all these spheres, we obtain new position of wavefront. At later time. Okay? At least the meaning is clear. Okay? Let us understand what it is trying to explain. Alright? So see, I cannot draw a sphere on the board. Fine? So assume that this is a spherical wavefront. This one. You also draw it on your notebook. This one. This is a wavefront at t equal to 0. What Hygen says?
That each point will have its own.
Each point will behave like a source. So how many points you see here? Infinite. Okay. I'll just take a couple of them. So we have 5 points, and all these 5 points will behave like a source of secondary disturbance. Fine. So it's a point source, so they will emit spherical wavefront like this. Or I'll just draw one sphere, okay, like this. So this is a source, so it will create spherical disturbance like this, okay. Now what it says, if you draw common tangent, what will be the common tangent to all these spheres above they are infinite in number? What it will be? Another sphere, find this one. One will be this, and another will be inner also.
One is past, one is future.
No, draw this first. This is called back wave. This is front wave. Okay. So Hygen has randomly assumed that back wave is absent. Okay. He hasn't given any logical explanation, but later on, very intensive mathematical analysis proved that back wave is absent. Are you getting it? So back wave is not present. So if back wave is not present, I don't need to draw the full sphere. Are you getting it? So I am not drawing common tangent backside. So I'll just draw part of the sphere, front, like this. Getting it? And direction of velocity of the wave will be perpendicular to the wavefront, like this. Are you getting it? So now this becomes new wavefront at t equal to t, and this is at t equal to 0. Getting it? Now what will happen? Each point on this wavefront will become the source, and we'll just keep on going like this. Fine? Any doubt? So its radius keeps on increasing. Once the radius becomes infinity, it becomes a planar wavefront. What if it is a planar wavefront already? This is a wavefront like this. I can assume, let us say, these points as a source. So I can draw a sphere of same radius, because after same time, same distance will be covered. So this is the new wavefront, common tangent. Fine? Like this. And suppose you have a line of, this is light, okay? It emits lights everywhere, okay? So how will it be the wavefront? Wavefront will be cylindrical. Fine? Each point on the cylinder will be a source. Fine? So like this, if you draw, now I am able to show only like two lines of a cylinder. How many lines are there? Infinite, and it is on this circular. So it will be as if small balls are attached on the entire lateral surface. When you draw common tangent, it becomes a surface. So it will be as if radius of the cylinder increased. Fine. So you can apply Hygen principle anywhere. Okay. Fine. So this is the fundamental principle of this chapter. Now what we are going to do, we are going to understand law of reflection and law of refraction using Hygen's principle. So we are using Hygen's principle to prove law of reflection and law of refraction, because we haven't proved it when we studied ray optics. Fine. Now we are proving it using Hygen principle. Fine. So first, we keep it Hygen principle only, the heading. We will first prove law of reflection. Write down. Okay, so suppose this is a mirror. Fine. I am proving what? Law of reflection so there has to be some reflection happening. Fine. So what I assume that a ray is coming like this, or let us say a beam of light is coming like this. So what kind of wavefront I have? Planar wave. If I do not have planar wave, can I say that angle of incidence is same? Angle of incidence will be different, isn't it? If it is not a planar wave, suppose it is spherical. Suppose the point source is there. So it will emit light everywhere, so light will reach like this, everywhere. So angle of incidence will be different. In order to keep angle of incidence uniform, I have to take planar, this thing. Fine. So assume that this is the wavefront of the wave that is hitting the mirror. If you have any doubt, please ask, because this is slightly counterintuitive. Till now we have studied reflection in terms of rays. First time we are studying reflection in terms of wavefront. Fine. So this is the wavefront. This is incident wavefront. Fine. Can you represent here where is angle of incidence? Show where is angle of incidence. Huh? No, actually make some construction and find out. You may know it already, but don't remember such things. Do it your own. How we define angle of incidence? Angle between incident ray and normal. Where is normal here? This is normal. And where is incident ray? Incident ray is a direction of velocity which is perpendicular to the wavefront. Getting it? So this is incident angle I. Fine. If this is I, this angle will be 90 minus I, and this will be I. So this is incident angle. Fine. Let's say this is point number 1 and this is point number 2. This point. Okay. Fine. What is the direction of motion of point 2? How it moves? Perpendicular to wavefront, right? So it will move perpendicular to wavefront like this and it will travel in this direction. And suppose it hits here. This is suppose point number 3. Okay? So by the time point number 2 reaches point number 3, where this point number 1 goes? Can you represent it? Suppose this is distance d. Can you draw it on your own where this point number 1 will be? If point 2 travels d distance, how much point 1 will travel? D only? Will the speed be different after reflection? Speed will be same because same medium. Fine. So if this travels d distance, this will also travel d distance. Are you getting this point? So if I say that I draw any random line d distance, I have drawn like this. This is d distance. Then I say that okay, this is no, I'll just a little bit. This is suppose 4. Then I say there is this point number 4. Okay, this point number 4 and what distance is also d. Okay, now same line I could have also drawn like that. You know, I could have said that this is d and this is 4. Are you getting my point here? So just knowing distance d is not enough. Can you tell me what should be this angle? How much it should be? Think of it, tell me.
So 4 and 3, 4. 3, 4 is basically the new wavefront, right? And D is the direction of propagation, so that should be 90 degrees.
90 degrees. Are you getting the point? This is the direction of propagation of wave. And this is a new wavefront, 3 to 4. So it should be 90 degree. So we have to ensure that when this line comes and this line connects, this angle should be 90 degree. Are you getting this? It should be 90 degree. So how to ensure that? There is a geometrical construction for this. for that, what you do, you take d distance as a radius and draw an arc. Fine. If you draw an arc, and when you connect, see the distance of any point on this arc will be d from 1. Are you getting this? But if you connect a tangent from here and then you connect this, then I can ensure that this is 90 degree. Fine. So this is how you ensure that it becomes 90 degree. You take an arc of D, draw it like this, and then draw a tangent and connect this. Getting it? So this is now distance D. This is a new wavefront. This is 1, 4. So 1 to 2 is older wavefront, and 3 to 4 is new wavefront. Or 3 to 4 is reflected wavefront, and 1 to 2 is incident wavefront. Fine. Can you show reflected angle is where? Where is reflected angle over here?
So 3K is a perpendicular angle.
This angle is reflected angle. Fine. So this is R. Now if this is R, this will be 90 minus R. This is 90 minus R and this is 90. How much will be this? R. Okay. Now can you prove I is equal to R?
So yes, sir. Similar triangles.
Similar, congruent triangles.
Congruent.
This side is common. This 90 degrees.
DD.
And what else?
Distance is D.
And DD. Okay? So these two angles automatically becomes equal. Okay? So we have proved law of reflection using Hygen's principle. Okay? Now we are going to prove law of refraction. The first law of refraction. That is Snell's law using Hygen's principle. Any doubt on this? Write down law of refraction using Hygen's principle. Now the light will not reflect and be in the same medium. Light will change the medium, and if light changes the medium, the speed changes. So by the time a particle travels a distance d, other particle may travel lesser distance. Okay? So let us say that this is the interface. Okay? This is the interface, and this is the incident wavefront. This one. 1, 2. This is the incident wavefront. Let us say this is, for the sake of simplicity, we can say this has refractive index 1 and this has refractive index of mu. Okay? In your book, they have taken N1 and N2. Yeah, they have taken N1 and N2. So we'll also take N1 and N2. So this is refractive index N1, this is refractive index N2. Okay? Let's assume for the sake of convenience that N2 is greater than N1. Okay? Now the direction of motion of 2 is what? Perpendicular. It reaches here. This is point number 3. Okay? Can I say this is the incident angle? I. Same thing. Fine. You can check similarly that this angle is angle of incidence. Okay? Now by the time 2 reaches 3, suppose this is a distance d, where 1 will reach? It will go down, right? It will not reflect now. So where it will be? Can you try to do this? I mean, see, the speed in second medium will be, of course, less, right? And you can assume V1 is a velocity in medium 1. What will be the velocity in second medium? So like that. N1 by N2 is equal to V2 by V1. Done?
K is a constant.
What is K?
So V1 by V2 is equal to N1 by N2 square. But V1 is equal to K N1 and V2 is equal to K N2.
Fine. So what we are trying to do first, you have to understand that. We are trying to find out by the time 2 reaches 3, where 1 reaches. So time of travel is same. Distance may not be same. So if velocity here is V1, then V1 into T is equal to D. Fine. So if velocity is V2 over here, V2 into T is what? Right? So we know that V1 by V2 is equal to N2 by N1. Is this clear? So V2 is what? V1 times N1 by N2. Right? So this becomes V1 tau N1 by N2 distance. V1 tau is what? D. So D times N1 by N2. So it is less than D, and I exactly know how much this point will travel. Right? So I will take that much diameter and construct a circle with this as center, right? Now what should I do next? Create a tangent from 3, isn't it? So when you put a tangent, like this is a point which is 4 and this is 90 degrees. Can you show angle of refraction over here? This distance is D times N1 by N2. This angle is R. How?
So you draw perpendicular.
Draw perpendicular over here. This is angle of refraction. So this is 90 minus R. That is R. Okay? Now prove law of refraction. Try to prove it. See, you have 2 right angle triangles and this side is common, 1 to 3. So you can write distance of 1 to 3 in terms of D and then in terms of this distance. So 1, 3 distance will be equal to D divided by sin I, isn't it? And this is also equal to D N1 by N2 divided by sin of R. Okay? D get cancelled. So sin R by sin I is equal to N1 by N2. Fine. So like we get N1 sin I is equal to N2 sin R. This is what the Snell's law is. Fine. So you can see that how powerful this principle is, Hygen's principle.